So Brandon grew up in Massachusetts and attended Union College in New York for his undergrad studies. So he's currently a sixth-year PhD candidate at the George Washington University in DC with a joint appointment at the University of Maryland, College Park. So his research is in the field of time domain astrophysics. And in particular, he is interested in the formation and evolution of high energy transients and their progenitors. So Brandon uses a variety of optical, infrared, and X-ray observatories to study these transient phenomena across the electromagnetic spectrum. And today he'll summarize his dissertation with this seminar. So welcome. Oh, by the way, before I forget, if you guys want to meet with him, talk to him, or have any questions, his schedule is pretty open. We sent the Google Sheet schedule on the announcement, so feel free to book an appointment. So welcome.
Yeah, thank you for the introduction. And yeah, if you want to meet, just come up and talk to me after, and we can find a slot. I'll be around for a few hours after this. So yeah, I'll be summarizing my dissertation research. Right. Thank you. Yeah, so summarizing my dissertation research, there's two main topics that are covered in my PhD. The first is focused on galactic X-ray transients discovered using the Swift X-ray telescope as part of the Deep Galactic Plane Survey. So I'll talk about that first, and then I'll transition rather abruptly to short gamma ray bursts and extragalactic objects, looking for the host galaxies and environments of these cosmic explosions. So first, some motivation for why we undertook the Galactic Plane Survey with Swift. So the first is discovery of new compact objects. We want to find new neutron stars, new black holes, high mass X-ray binaries, magnetars, these types of objects. And to do that, we need to do some sort of cadence survey of the sky at X-ray wavelengths. And that was the motivation for the survey. So on the left, we see an image of the galactic plane in optical wavelengths. The white square is essentially showing the region that we focused on. We ignored the central part of the galactic center just because source crowding is an issue there, and the background's higher, so we're not as sensitive to these faint transients. And the other motivation for these survey regions is that on the right, we see in galactic latitude and longitude location of known magnetars and high mass X-ray binaries before we carried out this survey. So these objects we're looking for do exist in this region, and we want to understand whether there are more in this region. So again, on the left, this is a plot of the Milky Way, and these blue shaded regions show our line of sight through the galaxy. We're going right through some of these spiral arms where we expect there to have been star formation rather recently, and some young sort of high energy objects. So in total, there were 380 tiles of 5,000 second each for a total of almost 2 megaseconds. And this is deeper than past galactic plane surveys at these energies. On the right, we see these tiles mosaic together. As I said, we ignored this central region of the galactic center where source crowding is an issue. So I wasn't able to make one giant mosaic, and this was the best way to sort of show these things. So you see some really bright objects around here. Yeah, you can see my cursor. So here, this is stray light from the source being sort of off axis to the instrument. And in these regions, we actually have to sort of throw them out just because the background is too high, and source detection algorithms would find, a rather high number of fake sources there. But you can also see a number of fainter sources in here. There's a few here, 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 here. And these are essentially like the 50 brightest sources we detected. In reality, when we run our source detection algorithm, we find about 1,000 X-ray sources in the images you were just looking at. And this is because Swift has a low background, and even 5 photons that fit within a PSF shape could be considered a detection. And 400 of these sources are actually new and unknown to other X-ray surveys that had been previously performed, showing that we're going a little bit deeper than some of these other surveys. But actually only 70 of them are classified. And we see on the left this breakdown into some classification. We have some known magnetars and high mass X-ray binaries, like I said, but also LMXVs and CVs, young stellar objects, about 5 AGN that are actually bright enough to be seen through the plane. But 70 out of 1,000 are classified. So there's a lot of work we can do here to try to identify what these sources actually are. And I think this is where machine learning and this kind of thing comes into play. But our approach was actually to look at the sources that have a flux greater than 10 to the minus 12 erg per centimeter squared per second, and which show variability. And we focused on individual objects using NuSTAR, XMM, NICER, and Chandra to go deeper and study these objects at different energies and different timescales, and look for periodicity, but also undertaking optical campaigns like spectroscopy to classify the optical counterpart if we can get a really precise Chandra localization. These are some of the sources that we've worked on, and just to give you an example of what sort of the timescales we look at sources were, Swift scheduling is sort of random, and so it's not like every month we observed. It was more like sometimes they observed the same region of the sky for 5,000 seconds in one day. Sometimes it took them 5 times to go back. And if they went back 5 times, then we can build a nice light curve like this and identify transients. So actually that was a really nice way to schedule these objects. So I was able to classify a new BE X-ray binary and identify a pulsar in NuSTAR and NICER observations. The magenta star here shows the location in the Corbett diagram of the spin period and orbital period of high mass X-ray binaries. Yes.
Sorry, what's a BE X-ray?
Sorry, a BE X-ray binary is a high mass star, a BE star, which is a BE star which has emission lines in its spectrum. These stars form decretion disks around them, and the decretion disk causes H alpha emission, which is where they get their name. Yeah.
Oh, I'm sorry.
Oh, sorry. These high mass stars are in an orbit with a neutron star. And as the neutron star passes through this decretion disk, they undergo type 1 X-ray outbursts. And we can then identify, based on getting many of these, the orbital period of the system. And in this way, we can classify them as what's going on. If that makes sense. The other object was a new polar magnetic CV. And this object, here's an optical spectrum of its counterpart. We see all these emission lines. It's really just a nice spectrum that we were able to get here from the Southern African Large Telescope. And one of the ways we classify it as a polar magnetic CV, besides the fact that we can take photometry of this object and identify its orbital period of about 3 hours, is that H alpha, H beta, H gamma, all these things are at similar flux levels. And this is what we call a reverse Balmer decrement. Because normally, if you're looking at galaxies or something like that, H alpha is generally much, much, much brighter. And in these systems, the physical processes reverse that. So these are 2 sources that I've classified myself. There's other sources we've classified from other people and that are undergoing work right now. This is just an example. So I'm going to transition now away from this first half of my dissertation towards the second half, which is on short duration gamma ray bursts. So these are gamma ray bursts detected by space satellites with a duration of less than 2 seconds. On the left, we see an example of GRB 170817. Here is the duration of here's the light curve detected by Fermi and integral. And LIGO Virgo, this is the in spiral signal from gravitational waves. And there's about a 1.7 second delay. And this is the first indication that these short gamma ray bursts were, or first confirmation, there have been other indications, that short gamma ray bursts are caused by neutron star mergers. And so what I focused on is, what are their host galaxy environments? Where are these binary neutron stars forming? Looking at really cosmological short GRBs that are at much larger distances than 170817, which was at 40 megaparsecs. But these systems can still tell us about the rate of these events, how binary neutron stars form and evolve, what type of star formation regions are they forming in, and whether or not they do receive really large kicks when they're born, which can make them move to large distances. And this tells us where to look when we're studying gravitational wave sources. Should we be looking near a galaxy? Should we be looking offset from a galaxy? What field of view do we need to look in? These are some of the questions this helps to support. And in fact, the offsets, the large distance of short GRBs from their host galaxies, was one of the early evidence that binary neutron stars were causing them before the 2017 confirmation. And on the right, we see an example of GRB 130912A. So this is an example of sort of what would look like an offset short GRB. We see a candidate host galaxy. Magenta circle is the GRB localization. It's a sub-arc second localization from an optical afterglow. And the distance here is about 3 arc seconds. So this is a pretty significant offset. But when we compute the probability that this is the host galaxy, we find that that probability is larger than 20%. So it's unlikely that this is the true host galaxy. And this is where we refer to it as a hostless short GRB. It doesn't mean there's not a galaxy candidate nearby, but it means probabilistically we can't say with high confidence that this is the galaxy. So there's a few reasons to study these hostless events, and this is what I focused on. The first is to confirm whether or not these hostless events are actually at large offsets from this galaxy, like for 130912A, which then tells us whether or not binary neutron stars have these kicks, how long the time delay between formation and merger is, which is really relevant for predicting gravitational wave rates. The other alternative is that they formed in high redshift galaxies that we do not detect even in Hubble images. So very high redshift faint galaxies underlying the exact position, not requiring a large offset, is the alternative. And this is pretty important because if we're saying that binary neutron stars occur at high redshifts, that means their kilonovae could have been responsible for populating the early universe with heavy metals. So these two scenarios are very separate and lead to very different predictions for gravitational wave rates and binary neutron stars as a function of redshift. And on the right is an example of GRB 160410A. So this is a spectrum of the afterglow of this GRB, which yields a redshift of about 1.7. Sorry, this is in the way. Hold on. Yeah, sorry. Here, the redshift is about 1.7. So this is a high redshift short GRB. And when we look in the optical here, we see nothing underlying its position. So we know it formed in a pretty dense environment because the afterglow emission itself displays Lyman alpha, which means it was in a pretty dense environment, but there's no galaxy that we see. So this is a really good example of an observationally hostless gamma ray burst, which actually occurred within a galactic environment. And it leads us to question whether or not there's other examples like this that exist. And the majority of short GRBs have redshifts come from galaxy association. So associating the galaxy correctly is incredibly important to inferring rates and energetics to these events. This is one of 4 or 5 that actually have a confirmed distance from the source itself. Let's do that. Okay, so I undertook a deep survey of short GRB host galaxies, focusing on those with no host galaxy and no sensitive search for a host galaxy. The motivation being that 30% of short GRBs with a subarc second localization have no confirmed galaxy association that is very strong. And we see here on the left that actually there are some that are just too sparsely localized to look for a galaxy. These are those that might just have a swift bat localization of a few arc minutes. They might have an XRT localization of, a few arc seconds or 6 arc seconds or something like that. It becomes very hard to say what the right galaxy is. So we threw those ones out. And we show that on the right. We started with swift bat short GRBs. We applied selection criteria such that it was localized less than 4 arc seconds, which is really where we decided we can say what the right galaxy is, because generally there's a few candidates around. And then we took optical imaging with the Lowell Discovery Telescope of all of these events. And if we detected something, then we took multicolor imaging or spectroscopy if it was bright enough to say, can we get a photometric or spectroscopic redshift from the galaxy association? Or if we don't see anything and we think it might be hostless, we want to use Gemini, Keck, HST, GTC, all these sort of deep, really large aperture instruments to look for their hosts. So in total, I studied 31 short GRBs. Adding this to those in the literature, there are now 72 events that satisfy our selection criteria that have been well studied. So essentially doubling the sample. And in total, I analyzed about 150 observations, imaging, and maybe about 20 spectroscopic observations to covering these 31 short GRBs. So not only did we double the sample of well-studied short GRBs host galaxies, but we double the sample of XRT localized events with hosts. So these are events that do not have a subarc second localization, and because they don't have a subarc second localization, we can't precisely say what the offset is. There's larger errors on this distance between the GRB and the center of its galaxy, but they still provide useful information like redshift, stellar mass of the galaxy, age, and these kind of things that are important on a population scale, just because there's not many short GRBs that happen every year. There's less than 8 short GRBs that happen every year. So we need to study all of the ones that we can to the best we can. So yeah, 72 well-studied events, 52 that now have a host galaxy, but still 20 that are hostless, despite this deep search with these instruments. And this is about 30% of the population that does not have a confirmed galaxy association. And this is sort of the interesting thing. So to begin looking at host luminosities, what their brightness looks like as a function of redshift, we have the R-band magnitude. This is apparent magnitude, not corrected for redshift or anything like that, on the y-axis. And on the x-axis is the distance, the redshift. We see that these short GRBs are essentially tracing these black lines, which are 0.1 to 1 L-star galaxies as a function of redshift. These are essentially the most massive galaxies at each redshift. So we're preferentially forming in really massive galaxies. But when we look above, when we look at these purple dots here, circled in red, these purple diamonds, sorry, are actually, these are the hostless ones. These are the magnitudes of the hostless ones. These are the ones that we can't say this is the confirmed host galaxy, but it's the most likely one because we can still compute a probability for all of the ones in the field and say the lowest probability, is the host. And actually, if we try to compare the magnitudes of the other ones, we find that they're probably above Z of 1. So in fact, we're finding possibly a missing population of short GRB host galaxies at higher redshifts, which would then imply that binary neutron stars merged very quickly and polluted the early universe with heavy metals. And one of the reasons we come up with for why these might not be really strong associations is just based on the way we compute probability. We compute a probability based on the magnitude of the galaxy and the distance from the center of the galaxy to the GRB position. And if you have a fainter galaxy, the probability that it's not the host goes up. So for faint galaxies, it's much less likely that you can actually say that's the correct galaxy. And this is sort of the problem and possibly a bias that led us to not find these before. So here's looking at the redshift distribution. So we have a cumulative distribution on the y-axis and redshift on the x. The black solid line is the redshift distribution for short GRBs. There's about 45 of them. And we have some different models for different delay time distributions, this being the time between formation of the binary and merger of the actual binary through gravitational waves. The dashed line is essentially a lower limit to the cumulative distribution of redshifts if we assume that those purple diamonds I showed on the last slide all have a redshift greater than 1. And in fact, it would imply that there could be a larger population in the early universe. The true distribution is somewhere between the black and solid black lines, the dashed black and solid black. And of course, the important thing to talk about also is the offsets, as I've been mentioning the whole time. So these are the offsets in red, this total work. For those with subarc second localizations, like I said, those are the ones you can compute precise errors that are generally quite small on what this distance is. And comparing it to the literature in black, there's not a large difference. So we've doubled the sample, but the offset distribution is still pretty similar. But having a larger number means we can start to split these things up by different properties. And one of the things we can do is split them up in redshift. So if we split them at about 0.5, there's about 12 of these above and below that have subarc second localizations, and these are spectroscopic redshifts of the galaxy. We find that those at smaller offsets in blue have about twice the median localization, median offset of those at higher redshifts. And this sort of goes to what I was talking about in terms of possibly this is a selection bias against high offset short GRBs at higher redshifts where the galaxies are fainter. And if you have a larger distance, the probability that this is the host, it becomes harder to associate it. Or this is a physical evolution in the location of binary neutron stars with redshift. And more work needs to be done to investigate whether this is the case, because that would also in itself be very interesting. And it could be an evolution of binary neutron star kicks or an evolution of their host galaxies. And it's not clear at this point. As you can see, we would love to have more redshifts of short GRBs so we can increase this. And this is where the need for really sensitive and fast follow-up campaigns in the optical and infrared for short GRBs becomes really important. And also, for example, Chandra to localize short GRBs to subarc second positions, because it's easier to detect them in the X-rays than the optical and infrared. So these are some of the ways we can try to improve on this. And here's my summary slide. Essentially, so the Galactic Plane Survey, we detected about 1,000 X-ray sources. About 40% of them are new. We're classifying these and working on classifying these, trying now to apply machine learning methods, because if you have 1,000 sources, you can't follow them up every single one. You can't get the resources to do that. It's very hard. And then on short GRB host galaxies, still finding 28% are hostless. They could be at higher redshifts. There's some indication for this. And there may be evidence for an evolution in their locations within their host galaxies. So thank you, and I'll take any questions.
Any questions from our in-person audience? Yep.
So do you worry that the gamma ray bursters, some of them might be gravitationally lensed?
That's a good question. I have not thought about that too much, but when we look at those that are actually in clusters, or that there are evidence for clusters being in that region of the sky, there's only a handful. So that's a hard question to answer, I think. And I don't have a good answer for it.
Question about this last graph.
Yes.
You mentioned regarding the physical interpretation. One way I can see the evolution can explain this is if you assume that these sources originate from global clusters, because generally with the evolution from redshift 1 to 0, the global cluster systems grow a lot because of mergers. They get more disturbed. So the orbits of existing clusters might become higher. And so the average distance from the host might be larger. So this might actually explain, if you can find a way of forming binary neutron stars in a global cluster, which I think there are many, like you can get that, like the primordial, the early formation, or you can get the capturing. And so on and so forth. So have you tried thinking about it?
Yeah, so there have been some studies of binary neutron stars in globular clusters, and I agree that this is something that needs to be considered. But since we haven't been able to confirm that there's any binary neutron stars associated with these clusters, it's been very difficult, and that observationally is quite hard, just because of the rate of events at low enough distances that we can really say that there's a globular cluster there. So that's really a tricky point, but I agree it's something that theoretically could totally be a possibility to explore.
So far, there have been 0 supernovas in clusters.
Yes. Yeah.
All right, other questions? Online. Any questions from our online audience? Please raise your hand or write in the chat. See anything? Last chance for final questions. All right, if not, we'll thank our speaker again. All right, we only have one speaker today, so that's it.